This is me. Most of that's been covered. The point I'd like to point out is the bit at the bottom, which is just that I'm not necessarily a smart guy. I just happen to be the guy who's at this end of the room. And I work for Huddle, so we're kind of a cloud-based alternative to SharePoint. And this is our agenda, right? So we'll talk a little bit about the hexagonal architectural style, right? And I'm going to open the conversation a little bit by talking about what architectural styles are, and then we'll try and describe hexagonal architectures within that kind of context. And that should roughly run you through what their properties are, when you might want to use them, what the benefits are of using that approach. Okay. Then we'll talk a little bit about implementing ports. Hexagonal architectures are also called a ports and adapters architecture more technically. And we tend to find when people talk about implementation that the ports are the bit everyone gets quite confused over and doesn't really understand how to implement. So talk about how we do that and what kind of approaches we use to implementing ports. And I'll talk a little bit about quality of service. That's won't be clear quite why I'm going to talk about quality of service towards the end, but it will become clearer as the talk goes on. By quality of service, I mean the issues like availability and performance of your software. Anyone read this? Software Architecture by Mary Shaw and David Garland. Okay, so Mary Shaw and David Garland, I don't know where they are now, but they were at Carnegie Mellon University in the 90s. So a lot of really good software engineering comes out of Carnegie Mellon in the 90s. And what Mary Shaw and David Garland really began to question was, what's the value in computer science? Okay, and that may seem like a strange question, but the problem is essentially that computing was happening without computer science. Computer science was a thing that happened at universities and most people just ignored it. And software engineering was going on quite happily building software. So the question they had is, well, do we actually have any value? Is there anything we do that really is affecting the industry? So they went to look back at understanding what science and engineering are for, what their relationship is. So one way to think about it is this, right? Let's say my dad and I make pots. We make pots and my dad teaches me the way of making pots. And he says, son, always use the red clay from over there. When we glaze the pots, we always do it this way. And when we build our kiln, we always use this wood. And the fire should look this colour when basically you fire the pots. And you should keep them in for this long. And you should always pray to the pot goddess and offer her a chicken in sacrifice. Right? And whenever I follow my dad's routine and recipe, I always make really good pots. So much so that the village basically says, don't farm in, you can just become the village's potter, pot all the time, right? And that goes on for a while, but eventually what begins to happen is I meet with other potters, perhaps I move to the town, we form a thing, like a guild or something like that, right? And we say, hey, this guy over the road, actually he makes his pots with the grey clay. And Mary, look at the way that she decorates her pot, that stuff's fantastic. If we got all of our ideas together, we could make really the best pots ever, right? It would be our kind of secret, but we know how to make the best pots ever. And so they take all this knowledge and they kind of accumulate it together and start to share it. So we've got sharing of knowledge, and we basically all start exchanging our ideas on how to make pots. And we have this body of knowledge which we say is, this is how we teach our apprentices and our journeymen to make great pots. And essentially this is pretty much the state of play for most people in software today. When we talk about movements like software craftsmanship, they explicitly reference this kind of journeyman, apprentice, master kind of model. And we say, hey, we're passing knowledge to each other. And if you take something like, Bob Martin's object-oriented software, agile software development book, that's a really good example of some kind of like, craftsmanship knowledge being shared amongst people. These are the practices we've used like solid, and these are the things that work really well for all of us, right? The problem is, we don't have much idea necessarily whether any of those things are actually really valid. Does solid really make any difference to the quality of the output of our software? Okay? Does praying to the pot goddess really make my pots better? Or does it turn out that I don't need to pray to the pot goddess and I get the same result? So that's what science is for, right? So when science creates engineering, it says, well, we're going to make a whole lot of pots without praying to the pot goddess, and a whole lot of pots praying to the pot goddess, and we'll figure out whether or not praying to the pot goddess is an important part of making decent pots. And so engineering is essentially where we take the ideas from craftsmanship and transform them through science into something that says, this is actually the best way to make pots. There's some science behind this stuff. So the idea that Shaw and Garland came up with and said, what we need to actually do in computer science is figure out whether there's any value in some of these engineering things that go on. Just kind of like almost tangentially, I read an interesting paper the other day. Someone looked at, who's read Bob Martin's Agile Software Development, either the Java or the C# version? Okay, a number of you have. There's a really interesting section there about, as well as the famous solid principles, there's a whole section of packaging principles he comes up with, and there's a really interesting diagram he shows of afferent to efferent coupling, and this thing called the main sequence diagram, which is where your components should lie. They're useful but not too abstract, and this is the perfect zone for it. Some guy did a whole lot of science on it and said, fascinating stuff, but it's complete rubbish. It's basically praying to the pot goddess. Okay, and so that's kind of this model. So the architectural styles piece comes from what Mary Shaw and David Garland did. They went away and said, we ought to be able to understand which architectures work and which don't work. And to do that, what we'll have to do is come up with a common description of those architectures, some way of defining architectures, architectural styles, and cataloguing them, and then determining how useful they are. Now, I won't talk about how useful particular architecture styles are and how they went through that. If you're interested, you can go and look at a thing called the candidate list problems, which are basically a set of a number of problems, everything from a CBOY to an ordinary website, and they discuss which architectures are suitable for which ones, and it's a whole field of computer science you can go and look at. What's kind of interesting from our point of view is this notion of being able to describe architectures in a certain way, and there's this notion essentially that all architectures can really be defined as components and connectors. Components are the locus of state and action, where we do things, and connectors are how the components talk to each other, right? And connectors tend to have a role. So client-server is a classic role between two components essentially, right? And those components, one is essentially acting to provide services to a range of kind of clients. Does that make sense? Anyone read Fielding's paper on REST? A couple of you. Yeah. And anyone read anything more than the chapter 5 and 6, which are actually about REST, right? So Fielding's paper on REST is most of his PhD thesis about architectural styles. So he's building on that work being done at Carnegie Mellon. Okay. So we can say, right, well, we've got these components, we've got these basically connectors between and we can describe any architecture as a series of components and connectors. So this is what Mary Shaw called a boxology, and she came up with basically a list of various groups and types of architectures. Okay, so some of the ones we'd be very familiar with is things like data-centered architecture or repository, which essentially says this architecture mostly consists of a component. There's a big database and a component. There's some kind of interface to that database, and it's like huge numbers of software applications essentially are that particular pattern. Data flow, pipes and filters, batch, sequential, which are essentially architectures about transforming work through a sequence of steps. Call and return, these are basic things like OO, that kind of thing. Very tracking process, event-driven, distributed, etc. One of the important things to remember is that we can have architectures that are both heterogeneous. What we mean by that is that it's turtles all the way down. So a given component, for example, in my pipes and filters architecture, I may have a filter, can be implemented in other architectural styles. So for example, it could be implemented by an OO language. Okay. So it's kind of an easy way of thinking about the breaking up of stuff. The one that we're most interested in really here are hierarchical systems. Okay. So hierarchical systems are a category of architectural styles, layered, CQRS, interpreters rule-based systems that essentially all have this kind of notion where we're trying to reduce the coupling by partitioning the system into a series of components. Okay. So layered systems, right. So just so you understand, hexagonal architectures or port and apps architectures are an example of a layered system. So they conform to the general characteristics you would have from any kind of layered architecture. So what are layered architectures? Well, in layered architectures we say, okay, software has a problem when it gets to a certain number of lines of code, right? I could probably write a reasonably maintainable program that had only 1,000 to 2,000 lines of code without really doing much software architecture. I could kind of just rely on the classic, main and subroutine style programming, and that would probably be quite maintainable. Right? When I get to bigger numbers, I start to basically think, well, that's breaking down a bit because I can't find all my subroutines. It'd be nice if I kind of cohesively put functions with the data that they operate on and cohesively put them together in blocks. So I start doing OO, and that gets me a certain number more kind of like lines of code. But at a certain point, it's nice to be able to say, well, I want to take a whole chunk of this code and say, you know, I can talk about that code as a thing, like shipping, or quite commonly we talk about, you know, people talk about data access and domain models as being things in layered architectures. That's not necessarily requirement. In fact, the classic diagram you see in layered architecture, one of the problems with them is this notion of saying presentation, service, domain, kind of infrastructure or data access is very naive and one size fits all, and actually you should break up your model a lot more. But you can say, well, I can cluster a whole lot of behavior and put it behind a stable interface. And that stable interface hides all those implementation details for me, right? So I say, behind here is something that's something useful, calculating my shipping costs. It may consist of a lot of interacting procedures, objects, that kind of thing. But I'm going to hide all that complexity away from you and have some kind of high-level, granular, coarser-grained interface that's very stable, that says something like, you know, pass me the two destinations, the destination and the origin that you're shipping to and from, the dates you want to basically ship, how quickly it needs to get shipped, and I'll come back with a route and some rough costings for you, right? And internally, we may have a lot of complexity, but that enables us to say, well, here we've got this reduction in abstraction, and that means that other pieces of our software, when they depend upon that abstraction, are depending on a kind of high-level abstraction, not implementation details. That makes it very easy for us to change the implementation details. If we're a shipping business, for example, it may be that one of our core competencies is developing better shipping routes, and that's how we beat our competitors. So that may be evolving continually, but part of the software which actually lets customers input their actual, you know, I want to go from A to B, is probably not changing that much. So it just wants to talk to a stable interface and get numbers back, whereas we want to keep iterating over our shipping algorithm and making it better and better and getting competitive advantage over our other competing businesses, right? So we have this nice stable interface, we have something in hiding abstraction. And the other advantage for developers is I don't necessarily have to worry about the complexity of the implementation if it's not what I'm dealing with. So if I'm the website guy and what I want to do is just really get the website up and get the customer's data in, I don't have to quite worry how the stuff behind this layer is implemented, okay? I just know I need to call it, maybe some other team entirely works on it, and I just basically say, I call this stuff and I get numbers back, and it's not part of my job to worry about that. And that helps us deal with greater complexity by dealing with these abstractions over problems, right? So layers are just examples of that particular idea, which is very common in software development. Hide implementation details, put a stable interface over the top. Object orientation has the same set of principles. And break it up into cohesive blocks, but we're coarser grained than, say, an object. Okay. And you can see here where would be a example of layering where effectively we've got some kind of core, you know, basic utility user systems, right? These are all just, there's no definition of what those layers need to be. Not sure anything. Okay. So we have a number of what we would call constraints on the components within a layered architecture. If we decide that the component, we're going to describe the component as being a layer, we can say, well, this component has this stable interface to it and hides some implementation details. That's where we actually do this work. There are some constraints we want to put on it. And one of the constraints basically we say is, well, this layer provides services, and it can be called by a layer above it conceptually, and it can call layers below it conceptually, but essentially it can't call layers above it. Why? We don't want circular dependencies because they're really hard to break. So if I call you and you call me, that creates a real problem for us in terms of our ability to maintain the software, because I change and you need to rebuild, but actually in order to basically get my binary changes, I have to rebuild, and that one gets built before the other, and then your builds keep breaking and it's a bit of a mess, right? So you don't want to do that. So basically you say, I need to provide services to the other layers. And that tends to give us something which is quite stable. So these invariants over the side are really just talking about that. So we get some useful properties out of that, right? We say effectively we're nicely decoupled, we've got basically increasing levels of abstraction, so we can basically break a nice complex problem into smaller pieces. We know what our interactions are. So because essentially I only interact with people above me or below me, I am either called or I call, it's pretty easy to reason about where we might affect people if we basically change our interface, or effectively if we want to, somebody else has, we want to call somebody else in a different way, etc. So pretty easy to reason about change. And we can swap things out. That's the user property. Right, how do you build? Don't worry about the small text, you only need to worry about the big text. How do you build a layered architecture? Well, it's pretty straightforward, right? So you say, well, what are my criteria for breaking up this large system into chunks? What are the things that this does that I can usefully think of as chunks of work that represent something where this part of the system calls this part of the system to get some operation done? Okay, and there is, this kind of standardized pattern that goes out there with presentation layer, service layer, domain layer, some kind of data infrastructure layer. You can use that. I would recommend thinking more carefully about what your particular problem space is, because your domain itself can be broken up by layers. And one of the things people quite often miss is the ability to say, rather than having an amorphous domain, you could break your domain up into a series of layers internally. That's one interface for each layer. So one of the hard bits is figuring out the granularity of the interface to the layer. But you say, right, well, this layer is my shipping algorithm layer. What is the API that essentially other services need from me? What is the granular stuff I need to expose? I want to keep that surface area as small as I can, and I want to basically make things that I don't think will change that often. And then essentially I can hide my implementation details that only really I need to understand behind that. You specify the communication between adjacent layers. Commonly, when we're talking about layering, it's a kind of in-process call between in the code, basically across the stack. Sometimes, essentially, we do have this notion of distributed systems being built with layers. We tend to work against that nowadays, and so that's not necessarily as helpful as some people thought at the time. So generally, you're talking about a kind of in-process model, and then you have to think about error handling strategy. What happens if I get an error in a lower layer? What happens? Is it do I surface it up via an exception that crosses layer boundaries? Do I swallow it at the layer boundary and decide essentially that I'm going to return to a kind of error code? You need to think about what's an appropriate strategy, right? We're not mandating anything. We're just saying those are the concerns that you will have. Okay. Disadvantages. Layers are not the layers are a useful organizing principle at a high level for code. They're not the only organizing principle at a high level for code, hence the idea of architectural styles. So for example, if I'm doing sequential processing, a pipes and filters approach is probably much more appropriate than a layered approach. So it's worth bearing in mind that this one size fits all of the kind of classic presentation, service layer, domains, etc. Doesn't really fit all. It fits a certain class of problems. The reason it's become popular is lots of things are just essentially website, database, domain model in between, right? And that's a very easy way of saying there are 3 layers here, sort of thing, with maybe an extra layer for a service layer. And that's why that model has become popularized. Okay, an example of layered architecture is ports and adapters. So ports or a hexagonal architecture is just a way of defining a layered architecture such that we have some additional kind of constraints, and we say here are some useful ideas about what layers could be involved, what are some constraints on those layers that have useful properties for us. Okay, that makes sense. Roughly everyone, I mean, most people have seen layered architectures, right? How many of you have implemented layered architectures that are kind of presentation, service layer, domain? Right, okay, really common. Just one thing to be aware of is those layers are not fixed by anybody, right? To do a layered architecture, you don't have to have those layers. You can have any layers you want, provided they are useful in breaking it up. Okay. Okay. Ports and adapters do define some layers, and we'll talk about what they are and why. Okay, ports and adapters were basically created by they're called Alistair Cockburn. Alistair Cockburn is also famous for a whole series of books about Agile. Probably one of my favourite Agile practitioners out there. My quick Agile Alistair Cockburn story is Alistair Cockburn was asked by IBM to go away and define the perfect methodology, the one that would basically reward them with basically successful software projects every time. Alistair went off into the research field and came back and said, Alistair, have you found this methodology? He goes, yes, I have. And they said, well, what is it? And he said, 4 guys in a room with a whiteboard. 4 guys in a room with a whiteboard always succeeds. And they said, Agile, the problem is, Alistair, this won't scale for many of our projects. You know, we want to implement this new Olympic site that we haven't got time basically for 4 guys on a whiteboard to deliver that. And Alistair said, well, that's where basically you get software methodologies, just attempts to basically make 4 guys with a whiteboard scale in various different ways, right? And so essentially, if you look at things like XP or Crystal, which is what Alistair Cockburn defined, they are just attempts to essentially make that 4 guys with a whiteboard scale. Right. He came up with this idea of ports and adapters. So the ports and adapters, here's a really easy way of thinking about it. It's very aligned with things like domain-driven design, because it says the heart of what we're building is our kind of domain model, right? That's the core of what we're building. So we're going to build our domain model here. Probably this notion of POCO or POJO is really important to us, or whatever the analogies are for whichever your preferred language of choice is, which is plain old Java object, plain old CLR object. What we're saying is we really want to minimize the dependencies between the code here and frameworks or other kind of libraries, right? As much as possible, this is kind of the basic code that you could write, you know, from your 101 textbook stuff without pulling in strange libraries. So no Java Enterprise Beans, no system.web if you're in .NET land, etc. If you live in Rails land, you know, DHH is probably wrong, and you want to start thinking about moving away from baking everything to active record, for example. Okay. But this domain model is something where you have a kind of clean set of objects where you can easily reason about them, don't understand the frameworks, and they're very portable across environments. Outside here on the edge, you have your adapters. Your adapters are how this domain model talks to the outside world. Your database, for example, if they want to basically persist stuff, or how your web front end calls your domain objects because you've got a user at some point tapping on a keyboard to call you, or at the end of a message queue where it's receiving messages, or it's a REST API that you're talking to. But this side represents data coming in. So we tend to divide this up into these little boxes, and the idea essentially, hexagonal comes from this idea of saying, because it's a shape that tessellates, there are multiple things coming in, right? So I just pick some ones here. So there's some feeds, so you might actually be putting out atom feeds or consuming atom feeds. You may have basically some kind of website. You may have a REST. You might be receiving AMQP, i.e. messaging, WebSockets, SMTP, etc. But all these things are adapters. They're ways of getting stuff in and out of your code, right? What you want to clearly do is make sure that there is no coupling between your domain model and these concerns. Why? Because you want to be able to throw this stuff away, right? Imagine, how many of you live in .NET land? Imagine you live in .NET land, right? And imagine that, the most in .NET land, you know what web forms is, right? So web forms basically is this kind of like, framework basically for building my website that Scott Guthrie and others basically came up with. Imagine a world in which web forms, as we discovered, wasn't the greatest way to build websites. Hard to imagine, I know, those of you familiar with web forms, you may think, surely Ian, nothing can replace this technology, it's the nadir of all website technologies. But imagine a world in which, say, an idea like MVC became very fashionable, and we thought we should have our own MVC framework instead of web forms. Hard to imagine, but bear with me. If I've written my code such that basically all of my domain model is baked into my web forms application code, for example, code behind handlers and that kind of thing, my problem is, if I decide to ditch web forms, that's really hard, because now I have to basically pull all my code out of the framework-based code, separate it out somewhere, and then put my new framework on top, right? And I'm really baked in, and this is what happens to a lot of people. They get trapped in a given technology stack because they're coupled so heavily between their actual domain code and the technology stack that they're using, right? Active record and Rails is particularly nasty problem area here, but Java, .NET land, we all have our own little versions of this particular nightmare, okay? So it would be really useful if we could say, actually, nothing in that technology stack should touch our domain code. The other way of looking at it would be, say, database, right? Again, in .NET land, imagine that Microsoft didn't only ever have one data access technology, but imagine they revved continually. Who knows? I mean, strange thought experiment. Imagine they revved, and every 2 years you had to deal with another way of accessing your data, right? Wouldn't it be nice if actually that data access framework wasn't baked into your domain classes, so that essentially you could just drop it and pick up a new one because that one was better? Okay. So the idea is to say, don't bake these concerns into these classes. They should be free of those concerns. So how do I, when I'm in this kind of like in my web front end, whatever I'm using, how do I avoid baking that in? So the idea is to say, well, I have this now thing called a port. This port is this layer here. And this port says, I am essentially a layer-led architecture. I'm a stable interface to what lies below, right? And all you do is you call me from your adapter layer, and I will exercise the domain model for you. I am this granular layer, this coarse layer, which exposes the domain objects underneath for you. I'm the thing you need to worry about. What happens inside is the implementation detail, but your dependencies on this layer. And that means essentially that if you ever need to drop your one website approach for a different one, for a different framework, all you have to do is just call this port from your new technology stack, right? So if you're in .NET land and you're worried about, wow, we know it's all .NET Core now and it's all ASP.NET 5, and it's a completely different ball game. How am I going to get there? If you built your site this way, you're not too worried, right? I just spin up a new a .NET 5 site, and I get to call my code through a port layer. It turns out there are lots of useful properties if we actually begin to push down this route. Okay. So this is an example here. Client posts, hits REST API, transformed basically into, by the adapter layer from HTTP into basically something we speak, i.e. .NET code or Ruby code or whatever effectively calls us, right? So what that slide is, right, port layer, we've kind of had that notion. The name port comes from the idea effectively of we can plug into. Right, use case boundary, might come back, so come back to that. Come back to that slide. Yeah, okay. So one of the other useful properties we get out of this is, it turns out that there are lots of ways we may want to exercise our code. And one of the ways we may want to exercise our code is tests. Right? But tests are just another way of consuming our code or exercising our code, and the same with our website is. So it turns out that what you can do is actually get your tests to call your ports layer, because then they're doing exactly the same thing the real code would be doing, which is exercising your code via the ports. And your test code doesn't really care about the implementation details. And there's a real problem if you couple your test to your implementation details, and that's that you can't do refactoring. Because refactoring is changing the details of your code effectively while maintaining a stable interface. So provided the interface remains unchanged, I'm permitted to go away and basically manage this stuff as much as possible, and no test should break. But as soon as my tests know about the implementation details, they'll break when I munge it up. But if you're testing about the ports, they'll work perfectly. Okay. We often refer to this area as the use case boundary. So it's the point essentially at which the behavior of the system is expressed. So for those of you aware of things like ideas like behavior-driven development, this is the kind of area where essentially you're saying, this interface here is what I'm exercising when I'm doing behavioral-based testing. Right? These things in here are implementation details about how I may deliver that behavior, but they're not the behavior itself. The behavior is expressed at the port boundary. Okay. You may hear notions about primary and secondary actors. So the idea of a primary actor is it says it's something where effectively I'm calling into the application, like I'm a REST API, and I call a kind of primary port, and it's kind of an input into our system. A secondary actor is a notion that our application sometimes will call out itself across a adapter boundary to something external like a database or messaging to another system, and that's basically called a secondary actor. That may not be that useful to you. Conventionally, we tend to show primaries on the left and secondaries on the right. Not that that tends to come out that often, right? It's a bit of kind of more esoteric knowledge for you. Ports and adapters architectures have some cognates. So Bob Martin tends to have something very similar called a clean architecture. It's very similar to ports and adapters. I think Jeffrey Palermo coined the term onion architecture. Again, very similar idea to ports and adapters. I really tend to use ports and adapters because it's kind of, if you like, the granddaddy idea behind all these architectures. All right, let's talk about implementing ports because I think that will help you understand the difficult bit. So, apologies to those of you that are on a kind of Java C# land. Hopefully you can do some mental translation for yourselves. How do you implement a port? So the classic way that this used to get done in loads of Microsoft literature, because it all follows kind of Martin Fowler, right? Fowler came up with this pan called remote facade, and he kind of said, well, what you need is an interface, not remote, so facade rather. What you need is an interface, and that interface essentially is a coarse-grained abstraction over loads of implementation data underneath. So really it's just a class with a load of methods on it, and that class load of methods on it essentially so that's what you call as the consumer, and behind it, it hides all the smaller level details, right? So I've got my class, my fat service, and probably a given class operates over one class of things. So I don't know, my customers or my employees or whatever effectively. So I've got my employee service or whatever, create an employee, update an employee, update an employee's salary, update an employee's NI number or whatever, right? So you have this kind of coarse interface which says, here are the things I need to do. And it's basically a facade. And that is the way that we have tended to do LED architectures for years, right? And it's not, it's actually, you know, it's all right. It's a stable interface. It hides implementation details behind it. It can remain stable, and we can basically make this reason about what's going on behind it. We can write tests against it. It's actually very workable, right? There's a reason why Fowler came up with it. There's kind of a few problems with it, though. One of the problems with it is that in implementation, these things tend to basically end up as 800,000 line monster files. And that's probably not what we want to do, because they're hard to read, and by implication, all that code in there, there's probably a lot of actual shared responsibilities going on rather than kind of one responsibility. So we've probably got multiple reasons to change in here. The other thing is we probably tend to find that if we're using dependency injection or some kind of approach like that, we probably end up with this hideous thing where the constructor has about 30 different dependencies all clustered in it, where we're saying, oh God, I depend on all these things, right? Rails had a kind of, you know, notion of skinny service fat model, which is kind of appropriate here. We need to slim this thing down, right? So what are some approaches we can kind of use? Well, the first one is basically this idea from the solid principles called interface segregation principle, right? And it says, as a client, say I don't want to depend upon parts of the interface that I'm not interested in. So if I'm the bit of the site that basically deals with employee salaries, I'm not really interested in stuff to do with name and address, right? It's irrelevant to me. If you change how you're handling name and address, I don't really care. So I don't want to be dependent upon those changes and have to go and, you know, retest my software, recompile parts with that kind of thing. So what I do is I can actually just expose a whole set of interfaces off my class, and you just depend upon the interface that you care about and call the relevant method. Right, that seems pretty good. Right, that's done some work. I'm done, I can go home. Fantastic. It's all done. That's kind of a first that people use. They break out these separated interfaces and say, I depend upon these interfaces now, so I don't depend on changes to your part of the class. It's kind of a lie, isn't it? Because it's still one class underneath. So if someone goes away and changes the implementation details in there, it might well ripple through to my actual, you know, interface, even though I don't really know about it. So the reality is we're probably going to have to test it.
One interface for one method.
Well, all right. Yeah, exactly. So then we say, well, actually, you know what? Single responsibility principle. Why don't I just basically say, create basically a class for each interface, with the methods on it than I do. So I've got basically a class for my, I update basically your address details. I've got a class for I update your salary details, right? And I can basically break all these things up. So eventually I've got my update, my service for food, blah, 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 right? Brilliant, that seems to work. And I've got single responsibility and I've got basically interface segregation. What a great idea. And actually, this is not a bad idea, right? This is a really good, stable way of breaking up my port layer into a set of individual things that basically represent granular operations on the model below. And I've broken this whole problem of, hey, I am affected by changes to this large global service because now I'm only affected by changes to things I care about. Right, so the unit of change is essentially one of these services, so the only people who are impacted are consumers. It turns out that's just a command pattern, right? So it turns out that the command pattern is an expression of this idea of saying, hey, I have this coarse-grained operation I want to perform upon my domain model, and I'd like to encapsulate the idea of performing this operation on my domain model. And I'd like to actually separate the invoker from the code basically that is called. So that adapter and domain model notion, right? I want to separate my adapter from the domain model. I don't want the adapter to know anything about it. And the command pattern clearly separates invoker and receiver. It says, separate invoker and receiver by having a notion of command. The command internally understands what the receiver is, who it has to call in order to execute this operation, but the invoker knows nothing about that. The invoker just knows, here's a command that I call to get that done. It's reusable. So it means that essentially multiple people in different endpoints can reuse the same command. And that goes back to the notion people were saying earlier of, hey, this is really hard. The translation between web forms and MVC never really seems to work. But in a command model it would, because essentially you're saying, well, I've got this command called, update your salary record for new NI number. And actually I can just call that from either web forms or anything else, right? I'm just actually issuing a high-level instruction to the back end to go and do some work for me. So you begin to break up your facade, you actually end up with a command design pattern as one useful way of breaking up your command. Those who are not familiar with it, you have kind of this idea of basically an abstract notion of a command with an execute on it. So that's something you can all basically teach an abstraction, and then you have concrete commands. Why do you have an abstraction over it? So you can essentially say that I'm not dependent on any one given implementation necessarily of a command. So what happens is the client gets registered with a command, it just calls execute, and so you could swap out for another implementation of it at some point. Right? That's the idea. And that's kind of the sequence. I registered my command, but now I've basically got this store command, and what happens at some point is I want to essentially execute this particular command, and I call the receiving code. Right, I think most of you have seen this at some point in your lives. Who's not familiar with the command design pattern? Is this new for anyone? Most people? Okay. One of the interesting properties of commands is that they are essentially transactional boundaries in the system. Right. So they say, here is something that I want to do, and when that is complete, there is a transformation. We generally think of them as transactional boundaries. So one useful pattern you can get into when you're implementing your command is to think about it having a number of steps inside it, right? It's kind of a formula for implementing commands. So the first thing you do is you want to begin some kind of transaction, right? And then you want to basically go away and load your state. So when you think about a domain models are essentially just rules engines, right? And what we do with rules engines is we say, initialize the rules engine with all the facts, and then basically run my rules, and I've got some kind of result. And domain models are very similar. You basically say, this is my domain model with current state. I load it from the database or whatever you've stored it. It may even be in memory. Then for my operation, don't worry about the term aggregate. That's a DDD term, but if you know what it means, it's useful. Otherwise, just you're operating on your domain model, performance for operation. Then you flush the transaction away. You say, save this transaction or roll it back if there's a failure, and you're done, right? So this notion of a command is this notion that's a transactional boundary into the system. So it's also useful when you're implementing commands, your ports layer, to have a transaction. Don't forget we also said that this was a use case boundary. Commands are very useful as use cases, as behaviors, which are often basically transactional units in our system. When you do this, it becomes very easy to reason about your system because you know where the transactions occur, where they begin and where they end and when they stop. And it may seem strange to say that's useful, but having dealt with some legacy code in my time that said, well, we'll use something like nhibernate, and we won't bother to turn on, you must basically only flush with a transaction. We'll just kind of let it flush whenever, like maybe when it throws an exception. That'd be useful to flush our current state to database, wouldn't it? So it's useful sometimes to actually have a pretty good understanding of where you're actually performing your transactions. Okay. One of the things to think about is, well, hang on a minute, what happens if I have some transactional boundary and I want to actually say that this command that affects this state here, I want to be eventually consistent to some things. That term makes it insensitive. If it doesn't, ignore this bit. You want to be eventually consistent and essentially just raise a new command, in the event, if you want that particular terminology, out of this and essentially say, hey, other parts of the system may care to now catch up with the result of this transaction that I've implemented, and you essentially do that as a result of your command here. If that's a model you're interested in. That means nothing to you, don't worry about it. Okay. Implementing a command, pretty straightforward. In other words, I have some kind of interface, basically. Originally, like I update something for my foo size method on it. It just simply becomes update thing for foo command with an execute method on it, which does the actual work, right? And generally what happens is you pass the parameters in basically the constructor, and then you just call execute, right? So think of commands like store procedures. They have parameters, and they do some work. They're a transactional boundary, right? Macro commands. Macro commands are, I want to do multiple things. I want to update your address and your NI number in one go. Macro command just says I have a list of commands and I execute them. Macro commands may have some functionality in them around things like rollback and reversing commands that were taking place in the event that basically you're doing multiple transactions. Right. Yeah, okay. We don't really want to get into this side too much, but in addition to commands for changing stuff, I'm going to get stuff out of the system. And that's essentially where we end up in this world of command query separation. We aren't necessarily into the world of CQRS, which is another layered architecture, but at the port layer, the other thing you may want to do is query your domain model. So as well as a command, you may want some notion of an abstraction of a query that says, hey, you can call my system effectively and get something out that represents the state of the system right now. Generally because I want to display it on glass being WPF, web forms, Rails, whatever it is. And so you're saying, actually query my model basically and return something that basically gives me back the state of the system. Quite often we talk about view models for this DTO. A notion of a view model retriever is quite often what people talk about. They say, this thing goes away and queries the state of the system and gives me back basically some kind of data object rather than a class. In other words, just supposed to set a state with no behavior that I can then use to basically return results to the end user. So command query separation is quite important. Command query separation is this notion that same applies on methods on a class. You either change state or you report on state. You never do both. If you do both, you have side effects, right? If I'm trying to get state but I change it at the same time, it's a side effect, makes you unpredictable. It's much easier to predict the notion straight to state of your software. When you call a port, you're either calling the port to change stuff or to retrieve stuff. Don't try and to change and retrieve in the same operation. It makes it very hard to understand what your software is doing. Okay. If you think about it, if viewing something causes it to change, that's quite problematic, right? We end up in the world of Heisenberg uncertainty principle and dead cats. Okay, you don't want dead cats. Make sense? Right. Let me give you show you a bit of code, because then some parts of this may make a little bit more sense. This one I think is the one we want. Yeah. Okay. So this is an implementation of command. So basically, this project it's on GitHub under it's called Paramore tutorial. A naming scheme I may explain to you down the pub, but not here. You can see that essentially it's got like a hexagonal architecture, right? And where we're showing that actually is we're just showing by folder structure some stuff going on. So here we actually have notion of some adapters, ports, the model. Don't worry about at data, it's just basically where our SQL compact framework database lives. Here in this one we've got adapters and ports. We commonly end up with this kind of implementation where we have a kind of core and then some kind of front-end component. When we begin to talk about these kind of implementations, that's quite often happens. But there's no requirement for that to be the way. You can have it all in one assembly. Just because, we'll show you later, you quite often reuse this bit of code. But here, what we want to show you is a command, right? So this command is basically, the notion of this particular example is some kind of top 10 task list, right? Where I go and I type my tasks in, and every day I can go and see what my task list is and by date. And I want to add a task, right? So I just create a command, and that derives from command. Our command object is basically just a very simple abstract class that has an execute method and just sets an ID for the actual command. And we pass in a set of parameters, right? The task name, its description, when it's due. We also pass in some dependencies for actually persisting stuff. When we call it execute, we just run through some code, right? We check validity of the actual information we've been given. We open up a transaction, save it as a database, right? This is a very simple model because it's an example. Obviously, you'd probably hope that in your real world, you'd actually have some more complex stuff going on, and you'd probably actually potentially have a factory for creating objects that held your access to your domain model. But here we don't have anything very much going on. Okay, that's a sort of pretty normal command. And I think we probably can show you retriever, which essentially does something very similar, just goes to the database, reads basically all the tasks, turns them into basically a DTO. This task list model, which should be really unexciting. It has some kind of markup on it for, it's producing basically a RESTful API, so it's producing some stuff like links and things like that. But it's kind of, the details of that are not that important, but we're just basically saying something we could produce as output for our HTTP endpoint, right? And
isn't that binding your model to the use of XML?
that returned value would be considered something we can, because it's coming out of by the port, it's something we consider part of the adapter layer, right? Sorry?
I was the one asking.
Okay, yeah, so basically what happens is the view model retrieves a port, it queries the whatever underneath that we can care about, and what's coming back out is really part of our adapter layer. It's technology specific potentially because...
So the word model here isn't because this is in the domain model?
No, it's essentially a model as in it's a view model, etc. Right?
Okay.
Yeah. If you want to see our actual model of tasks and stuff, it's kind of in here. It's not very exciting because it's an example, but that would be where our domain model code lives. Right? So we separate between the task there, which you can't expose, and the task model, which is exposed to the outside. Great question.
The word model confused me because
Yes, model like service is one of the great overused terms of software.
you need a manager.
Yeah, you do, yeah. Okay, that make rough sense how you'd use a command? Roughly, and in calling it, I'll show you how you call it. So this, just for example, this is actually using a web HTTP framework called OpenRaster, which is unimportant, apart from the fact that what you can understand is this is the endpoint of our code that is called in response to a RESTful API call, and you can see we've got markup on the various methods to say this is a get or a post or whatever. But you can see, for example, in the post here, what we're doing is just taking the parameters that come from HTTP, transforming them essentially into parameters onto our command, and then calling our command, right? We have no notion within this adapter, this endpoint, essentially of how that is implemented on the domain model. We just say, here's some parameters that we've marshaled out of the HTTP request body. We're turning them into basically parameters on this command object. We're going to execute it, and that will give us our required functionality. And the point is I can move that to Web API tomorrow with a relative amount of ease, because there's no real difference between Web API and OpenRaster and calling a command and executing it. Right, so we kind of separate ourselves quite cleanly.
Often it is valid. Why is that not just the same as calling a function with 5 arguments? You make a thing with 5 arguments and then you call a method on it.
So as we expressed earlier, the problem is that you want a stable interface for your port. In other words, people can depend on it, right? So let's say you end up with this command model at the end of it. But yes.
I work in functional programming, so it's like you
Right.
just have a function, right?
Okay, so yeah, essentially this is how OO creates a functional model, right?
Okay.
Agreed.
I've forgotten that.
Okay. The reality is that this notion that essentially I could swap my implementations, so that essentially rather than calling that add task command implementation, I called another one, for whatever reason, I don't know, we said that one's going to use Oracle or whatever, is a bit false, because we have this dependency on the concrete command. So what we really want to do is break that if we can, and say, actually, we really do want a world where effectively when I issue the command, I don't have any dependency on the implementation at all, right? So it's not a concrete implementation, which is hiding the received code from me. I actually would like at runtime you to figure out who basically satisfies this command. That's what dispatchers are for. Dispatchers say, let's separate our command into two parts, the parameters and the execution. And what we'll do is we'll pass the parameters as an object into something that says, I will go away and look up who basically can respond to this command and give them that object. It will then basically execute. So essentially we just split that class in two, and so take the execute half and put it in a class, take the parameter half and put it in a class, and put a new class in the middle. It's more or less an abstraction for programmers, right? This one will then find a registered class to basically deal with that. That's what dispatcher does. Dispatchers are useful because they really give us that clean separation that says, not only am I divorced from my adapter framework here, but my adapter doesn't have to actually know how I choose to implement it. So I can swap stuff. So here's a way we use this all the time. For example, let's say I want to basically work on a story that essentially modifies an existing where an existing command works. But I want to have the ability to work on master, right, rather than feature branching. And so what I want to do is say, well, actually what I want to do is create my command 2. In my command 2, I'll go away and change stuff. I can test that, I can basically write my tests against that particular command and check that it all works. I can keep checking into master. I can deploy to production at a moment's notice because nothing is currently farming its requests out to my command 2. It's all being farmed to my command. I'm just basically got a copy in parallel. When I'm happy that this one works, I could then say, right, now in production, I'm going to start calling this one. I'll keep the old one here, and potentially I've got something like a feature switch in config, and that means I could deploy to production. If it stops working the way I wanted it to, I can flip a switch in production and actually say, right, call the old one now. Okay. So this is genuinely useful basically in deployment scenarios to be able to say, you know what, I want a hot swap between who is actually handling this command. Okay. So how dispatcher works. So you have some kind of command dispatcher that lets you register and remove handlers. So you say, hey, this handler responds to this command. Hey, this handler no longer responds to this command, as you would think. And execute on it where effectively you pass it the command and it goes away and figures out who actually deals with this information. A concrete command handler, because we have to have abstraction. So this is the abstract one we deal with. This is the actual implementation. And that actually calls a given command handler. Generally, you have to have some mechanism to agree which command maps to which handler. This has a notion of the classic pattern of get key. In other words, essentially, we define a key that we share on both. In reality, we tend to use runtime type information. So we tend to actually say, well, look at the RTTI of this command and map to something that basically picks that up basically when it runs. So if this is my command, then look for registered handlers that map to basically a type of my command. Right? That's how I tend to do it in reality. But you could use a GUID, for example, if you wanted to. Right? Doesn't make a difference. And essentially the way it works is client registers a handler, and then what happens is it's this whole get key exchange to say, well, I need to find the key that you register that for lookup. And then what happens when I want to basically invoke something, I say, well, send the command to the command dispatcher. It figures out what the key for that command is. It then says, well, I need to go and look up the relevant handler. I've got the parameters here, and I'll pass it across to the handler method. Right? You'll see some example of code. It's very clear. Right, those of you living in the lucky world of .NET land, we have 20% time at Huddle. we produce a library called Paramore Brighter, which does most of the heavy lifting around this for you. Those of you not living in our land, if you live in Python land, you've got Celery. It's a reasonable facsimile of what we do. If you live in Java land, Hystrix is kind of in this area. If you live in other lands, I have no idea. Okay, so if we go and look at this, what we've just done over here is use our library to implement the same example. So you could put it the other way. We have a full example in the source code for Brighter around this task system. So it's got a UI and everything like that here, right? You know, I didn't write the UI, I'm used to UIs, but one of the guys in the team wrote a UI for it. But you can kind of see that what we have over here is in task list, the same endpoints. So again, it's just a open raster endpoint. And here what we were doing is pretty much the same thing we were doing before. We create the add task command, but rather than it calling execute, we send it to this command processor. That's just dependency injected. And it then goes away and basically deals with the command. You're not worried about how that's implemented, but what you are interested in is basically saying this. You've got an add task command, which kind of looks like this, all right? So it's still got all the parameters, got this validation method on it so you can validate the parameters are correct. And you've got a handler. And this handler here essentially says, I have a handle method on it here. Let's move that aside. So basically it derives from a base class that we provide, but don't worry about that either. But you have a handle method which takes in the command and performs the operation. It's just the same operation we had before. Whereas before, essentially, we were just doing on the execute of the command, which also contained all the parameters that work. Now what we're doing here is we're saying separate between this which contains the parameters and this which calls the handle. And in between, the library framework does basically dispatch for you. It says, go away and find things you've registered with me which handle that particular command. Make sense? The attributes we'll talk about in a second. Everyone still with me? Okay. All right. About quality of service, briefly, how am I doing for time? All right, quality of service, we'll run through some of these slides at a reasonable pace. We'll point some directions that you may want to go out and find stuff about. Okay, one of the things we actually let you do, well, that's rather irrelevant. Okay, most of us today are working with a distributed system of some form or other, right? Even if you don't know that you are, because a distributed system is just where you have two processes involved in your operation. So for example, if you have a database and a website, you have a distributed system, because there is a problem between your website and the database, which is one of them may not be there when the other one needs them. Generally, in the case of website and database, it's your database is not there when you need it. It may be there only, not be there only transiently. Why? Well, that's what we call the fallacy of distributed computing. There are lots of reasons why, essentially, you might be there not transiently, someone's deliberately moved it. We are doing a failover between Windows High Availability cluster elements because we've done some kind of like upgrade. We suddenly have just a blip on the network, which means for some moment the IP address doesn't seem to be there, and then it's back again, right? So things are unreliable in distributed LAN. When I call between two processes, it will fail at some point. And the notion that programmers tend to have of, it's okay calling my database, it will succeed, or calling another process, it's called the fallacy of distributed computing, right? This idea that these operations will tend to succeed. So what you need to do is plan for the possibility that they will fail. Now, there's a really good book by a guy called Michael Nigan called Release It. And if you're interested in this topic, you should go and read Release It. Release It's all about the problems that real production sites have when essentially you get into the world of distribution. Particularly in e-commerce. You work in e-commerce, you need a lot of experience with that. So generally there are a number of classic patterns we can use to deal with the problem of distribution. The first option is timeout, which says, okay, the first thing we need to be aware of is that because it can fail, we don't want to wait forever. Imagine the scenario in your website, essentially, where your code essentially says, well, I'll wait forever for the database to be up. If you've got a threaded kind of web server, then what's going to happen is thread 1's going to come in and wait if it's down. Thread 2's going to come in and wait. Now, sooner or later, you're going to consume all the threads available on your web server, and you're going to stop responding to requests for traffic. And those things are going to wait there forever until you reboot the server. Be much better if they timed out and you gave some feedback to the user and said, oh, you know, busy or whatever, right? Or control that particular problem. Apart from you can serve stale data, it's another way of solving the problem. Just say, well, it probably looks the same as it did 5 minutes ago, don't worry about it, right? That's quite a common policy. But you should always time out when you're making a call between two processes because they can fail. If it times out, what should you do? One option is to retry. Many errors are transient. So for example, a deadlock in the database. I get a deadlock, right? I need to time out. I need to basically say, well, I don't want, one of these is going to have to fail eventually, otherwise we're just going to sit there for eternity. So one of them fails, it times out, and basically we may be able to just retry the operation because someone else may have freed the locks that we previously wanted. Right? So retrying is a very common strategy to use to failure. Circuit breaker. So the problem with retry is you can end up flooding your own system. Right? So the problem can be that something goes wrong and a component's under strain. And because it's under strain from heavy load, a whole load of stuff basically times out because it can't get in because it's dealing with so much load. One of your problems is then you say, well, hang on a minute, I've got a problem getting to the database, I'm going to retry. That's just increasing your load. So you're now basically making your own problem worse. So the idea of a circuit breaker says, if I can't talk to a component, at a certain point in time, what you want to do is essentially, I can never remember if it's open or close or circuit breakers. You want to, for some reason, you want to basically, I think, open the circuit essentially and say, hey, I don't want traffic to go through right now. Anyone calling you gets an immediate failure. And then after a certain amount of time, you say basically I'm going to half close it, let some traffic through, right? And if that succeeds, then I'll let everybody through. But it stops you in the event of a problem on, say, your database server of your own attempts to retry making that problem worse. And meantime, all the things that you reject have to do something useful, like, say, busy, serve stale data, whatever, right? So it turns out that if we separate between our command and the thing that basically deals with the command, we can actually use that to help us with some of the characteristics of what's called a command processor. So a command processor is a simple pattern, says, well, if I pass my command to some intermediary, it can do work that is orthogonal to the main operation, right? By orthogonal, we mean if my objective is to add basically a new task to the system, orthogonal stuff is stuff like retrying the operation because it failed due to network issues, stuff that the domain model doesn't care about. And this port boundary, it turns out, is a really good place to start handling that because it understands the concern about saying, well, I'm calling out to my database across a port boundary so I can handle the mechanics of what happens beyond. My domain model doesn't really need to want to understand, right? Because I don't want to bake that logic into my domain. I'd like to bake that logic into my port so my domain is free of understanding the notion of distributed systems, etc. Right, that's my question. So we would show you a quick example. I'll show you quickly that we provide some support for that. So what we do effectively is provide these attributes. So that's one way of doing it. You could do it in lots of different ways. But we say, well, actually, this command can be given attributes which basically help it deal with those kind of issues. And we basically use a library called poly, which essentially lets you define policies for how you will actually do work. So that retry policy, I think, we'll find we set up somewhere in the configuration. Cross-domain pipeline configuration? No. Could be. I need to find where I do that. Okay, here we go. Don't worry about where we're doing it. That's kind of an open raster dependency, but you can see we're creating some policies here and retry circuit breaker registry. And oops, daisy, too fast. If you look at the code here, what that's actually saying is, hey, you know, I'm going to do a retry at these millisecond intervals, for example, or I'm going to circuit break after one exception, and I'm going to basically allow someone back in to test it after that number of milliseconds. The details are unimportant to you right now, but the idea is essentially you can see that a port boundary is a really useful place to separate your code from the quality concern of how you actually then call external elements. So you don't bake that logic into your domain, you can just bake it into the port. Okay. you want to understand who does this? So Hystrix is a really good example of someone using this approach. That's Netflix's basically underlying implementation library. It's all open source and it lives in Java land. Okay. We've done that, shown you that bit. Okay. If you go and look at our documentation for this stuff, you'll find we've got lots of documentation on hexagonal architecture. I can show you that, I think. If I do this, get out of the show, and flip over here, you can see here's our documentation. It's exciting. I don't know why I haven't got any sort of scroll bar. It's off the edge of the screen. What a nightmare. Wow. Okay. Hurrah, I have screen of some sort. You can see we've got a whole set of sections, and one of the things we talk about is there's a whole set of information about ports and adapters architectures, kind of how they work, some links to other material about them, and as well as stuff talking about a lot of stuff, topics we came up with basically in this talk. We cover off in that particular documentation. So if you want to go away and read this at your leisure, that's a really useful place to go to try and understand some of the stuff we talked about in the slide deck. Okay. There's also details about the actual project in there, but even if you're not interested in the actual project, if you want to understand hexagonal architectures, we've got quite a bit of documentation on the site about where they are and how we relate to them. Okay, that's me done.